You know all this incredible AI we're surrounded by? Well, there's this massive, hidden problem, a huge energy suck, and it's not where you'd think. It's not the thinking, it's the traffic. So today, we're going to dive into this really wild idea. What if the network itself, the routers, the switches, what if that became the computer?
All right, so here's what we've got lined up. First, we're going to unpack this hidden traffic jam in AI. Then, and this is the really cool part, we'll see how the problem itself actually becomes the solution. We'll get into the nitty-gritty of how you can actually teach a router to think, look at the proof that this isn't just theory, and then we'll look at the future. We're talking about brain-scale AI. Let's get into it.
Okay, so let's start with this big problem. AI's hidden traffic jam. I mean, we all see how powerful AI is getting, right? But all that power has a cost, a really big one. And honestly, we're starting to hit a major energy wall.
Okay, get this. This number is just wild. It can take up to 80 times more energy just to move data around inside an AI system than it does to actually do the math. Think about that for a second. The real energy hog, the real villain here, isn't the thinking. It's the constant talking between all the different parts.
So what's doing all this talking? It's something called the interconnect. You can just picture it as the nervous system of the AI. This huge web of tiny wires and switches that connects everything together. And in these giant AI models we have today, this interconnect has become the #1 problem. It's the biggest bottleneck, slowing things down and just guzzling power. And this chart just lays it bare, doesn't it? I mean, look at that. The bar for actual computation, the thinking, it's tiny. And then you have this massive bar for communication. It's insane. What this means is our energy utilization is terrible. We're basically throwing away most of the power just moving bits and bytes around. It's a huge waste. Okay, but here's where things get really, really clever. This is the big twist in the story. A group of researchers looked at this massive bottleneck, this huge problem, and they didn't see a problem. They saw the solution. They thought, what if we stop fighting this and just repurpose the whole thing?
And that led them to ask this kind of crazy but brilliant question. What if the traffic jam is the computation? Seriously, what if all that energy we're wasting on moving data around, what if that movement itself could be the calculation? And boom, that question gives birth to this new idea, processing in interconnect, or as they call it, pi squared, which is pretty cool. It's a whole new way of thinking. The big idea is you stop fighting the network and you start using it. You take the fundamental things that routers and switches do every single day and you repurpose them to do AI math.
This slide just nails the shift in thinking, right? The old way on the left, the interconnect is just overhead. It's this annoying, power-hungry thing you have to deal with. But with the pi-squared thinking, the interconnect is the computer. The problem literally becomes the solution.
Okay, I know what you're thinking. How in the world do you teach a router to think? Like, how does a networking box become a neural network? It sounds completely out there, I get it. But the way they do it is actually kind of beautiful.
So here's the magic trick. The researchers figured out how to map the basic building blocks of AI onto stuff that network hardware already does all day, every day. So check this out. In AI, you need to multiply, right? Well, in networking, you can just delay a packet by a certain amount of time. Same thing. You need to add things up? Well, you can sort packets by when they arrive. And what about that crucial activation step in a neuron? Easy. Just drop any packet that shows up too late. It's brilliant because it's using the language the hardware already speaks.
And you know what the best part is? They don't have to invent some brand new crazy hardware. This whole thing runs on existing, super optimized Ethernet protocols that are already in the switches you can buy today. They're using features like asynchronous traffic shaping and credit-based shaping. These are standard tools to mimic exactly how neurons work. It's a software and logic trick on top of hardware that's already out there.
All right, so this all sounds amazing in theory. It's a fantastic idea. But does it actually work? I mean, for real, can you get a network switch to do all this and still get the right answer at the end?
Let's boil it down to this. Can a piece of networking equipment, something designed to move packets, actually go head-to-head with a dedicated AI chip, a GPU that was built from the ground up for this stuff?
Well, you're looking at the answer right here, and it's a huge yes. Look at these numbers. They tested it on the classic MNIST dataset, recognizing handwritten numbers. A standard model gets 97.2% accuracy. The pi-squared network, 97.34%. It's actually a tiny bit better. Even a simulation of it is right in the same ballpark. It's not just close, it's spot on.
And just so you don't think this is a toy example, they didn't stop there.
They threw a much harder problem at it, a big model called ResNet-9, running on a complex image dataset. And the result? Over 94% accuracy. That's competitive with standard hardware. So the big takeaway here is, this thing scales. It's not just a cute trick.
Okay, so we've established the concept. It works, it's accurate, it scales. Now, let's zoom out, because the implications of this is where it goes from being a cool research paper to a potential revolution for the future of AI.
So the researchers did the math. They projected out what this could mean down the road. And their estimate for the power needed to simulate something on the scale of a human brain is less than 570 watts. Let me say that again, less than 570 watts. That's less power than a high-end gaming PC uses to run a new video game.
And this chart just shows how mind-blowing that is. To simulate just 1% of a brain with today's tech, you're looking at, well, tens of thousands, maybe hundreds of thousands of watts. It's a data center level problem. With pi squared, you could do the whole thing, 100 times more computation for a tiny, tiny fraction of the power. The difference is just staggering.
You know, maybe the most powerful part of this whole idea is that it's future-proof. It's not some one-off custom chip that will be obsolete in a year. It's built on networking tech. And networking tech is already on this incredible upward curve. Performance basically doubles every 2 years. So pi squared just gets to hitch a ride on that rocket ship for free.
And this quote from the researchers really just nails the whole idea. With pi squared, running an AI isn't about brute force math anymore. Multiply, add, multiply, add. Instead, it's about this much more elegant dance of signals moving through a network over time. And when you think about it, that sounds a heck of a lot more like how an actual brain works, doesn't it?
So that leaves us with this one big final question to chew on. For years, we've been trying to build the future of AI by making faster and faster chips. But what if we were looking in the wrong place? What if the next giant leap forward was never going to be in the chips, but was hiding in plain sight this whole time, in the very network that connects everything together?